Dear student, welcome. Today we are going to start hydrogen spectra. And before starting hydrogen spectra, now we are going to revive Bohr's atomic models formulae for different cell, how it was derived and what was the final result. According to Bohr's atomic model, energy of nth orbit was minus mz square for 4 8 epsilon square n square h square. This is the derived formula, and the reduced formula is z square by n square minus 13.6 electron. We must have to remember that all derivation made through assumptions of Bohr was applicable only for hydrogen or hydrogen-like atom. All formulae derived by assumptions of Bohr is applicable for one electron atom only, that is for hydrogen atom or hydrogen-like atom. What is hydrogen-like atom? Atom having equal number of electron as hydrogen, but in an element which is natural occurring has no one electron. This hydrogen-like electron is not natural occurring element, rather ion having one electron. Helium having atomic number 2, if one electron is removed, there will be left one electron. So one electron. Lithium having atomic number 3, if 2 electron removed, 1 electron left out, that is 1 electron. Beryllium having atomic number 4, if 3 electron is removed, there will be only 1 electron. So these species containing 1 electron and hydrogen intrinsically naturally containing 1 electron. So all formulae of Bohr's atomic model applicable for either hydrogen or for hydrogen-like atom. Whenever hydrogen-like atom pronounced, must have mind it will be either helium plus or lithium plus plus or beryllium plus plus plus. In case of hydrogen, the formulae reduces to energy of nth orbit minus 13.6 electron volt by n square, because z is equal to 1. If it is applied for helium, 2 value of z 2 must be operated. If it is for lithium plus and beryllium plus plus, then value of z will be subsequently 3 and 4. Now it will be quite easy to understand hydrogen spectra. In case of hydrogen or any other element, if electron jumps from one orbit to other orbit, as many as electromagnetic radiation absorbed or emitted as number of jumping possible. If electron is present in n is equal to 1, 4 and 5. Anyhow, electron is present in excited state, that is in 5th orbit. If supply of energy is stopped, electron finally jumps to 1st orbit. And now see how many way of electron present in 5th orbit they can jump to ground state. From 5th orbit, there is 4 options of jumping. They can jump to 1st orbit, or to 2nd orbit, or to 3rd orbit, or to orbit. That is, electron in 5th orbit has 4 options of jumping. And if there is 4 options of jumping, each and every jumping results in emits of energy, and a specific electromagnetic radiation will be emitted having certain wavelength lambda. Now if electron comes to 4th orbit, there is 3 chance of jumping. They may come to 1st orbit, or to 2nd, or to 3rd. Such a situation, 3 electromagnetic radiation will be emitted. When electron is present in 3rd orbit, they have only 2 options to jump. and in second orbit only one option is there. So total number of electromagnetic radiation emitted when electron was present in fifth orbit, then total number of emission spectra is 4 plus 3 plus 2 plus 1, and hence we have a formula: maximum number of spectral line, any one specific electromagnetic radiation is termed as a spectral line, is equal to n into n minus 1 by 2, where n is number of highest orbit in which electron was present. If n is equal to 5, then maximum number of a spectral line will be 5 into 4 by 2, 5 into 4 by 2, that is equal to 10. And from figure it was clear, 4 plus 3 plus 2 plus 1, it was also 10. If n value is quite high, 10, 20, 100, then by making the figure we can't calculate, we have to apply the formula. And now hydrogen spectra. In case of hydrogen atom, if electron jumps in many ways, electromagnetic radiation emitted, and final categorization of electromagnetic radiations or a spectral line was made on the basis of n final, and on that basis we have Lyman series, Palmer series, Paschen series, bracket, Hunt series, and Humphreys. Of course, in Lyman series n final is 1, Palmer series n final 2, Paschen n final 3, bracket 4, Fund 5, and Humphrey. During jumping of electron, as gap of subcell increases, number of cell increases, energy difference will decreases, resulting in wavelength. Consider it delta E equal to Hc by lambda. If energy difference increases, lambda will be decreases, and vice versa, because they are inversely proportional to. The one most important thing is series limit. Series limit is those two electromagnetic radiation, one of which has longest wavelength and one of which has shortest wavelength. As for example, we have taken Lyman series. So infinite radiations will be possible in Lyman series if electron finally jumps first orbit, either from second or third or fourth or so on from infinity. These all lines lies in Lyman series. So infinite, out of these infinite lines, one wavelength having the shortest and one wavelength is the longest, and in between this shortest and longest electromagnetic radiation, all infinite lines lie. How we can calculate lambda longest and lambda shortest, which is termed as series limit. Lambda shortest and lambda longest is termed as series limit. So let us consider lambda shortest. For lambda to be shortest, delta E must be maximum, and for lambda to be longest, delta E must be minimum. Change in energy, difference in energy must be minimum. ध्यान से देखिए, if lambda is to be maximum, energy difference must be minimum, and if lambda is to be maximum, the longest value, delta E should be. And we have already Rydberg-Balmer equation, which is about to calculate the wavelength 1 by lambda equal to R, and in case of hydrogen can neglect Z because its value is unity. R Z square means 1 का square, उसको neglect कर दिए, 1 by n initial का square minus n final square. So now for Lyman series, what is the lambda longest and lambda shortest? Let us consider the case. Lyman series was taken as consideration where n final is equal to 1 and n initial equal to 4 and so on. This for this series, if we have to calculate lambda longest, this will be equal to r 1 by, for lambda to be longest, previously we have already discussed, lambda should be longest if energy difference is, and when electron jumps from 2 to 1, energy difference will be, if jumps from 3 to 1, slightly energy difference, 4 to 1, slightly energy difference increases, and the maximum energy difference when electron jumps from infinity to first orbit. Means for lambda longest, delta E should be minimum, and from this can conclude n initial must be 2, and for Lyman's series, n final has only one possibility, 1. N initial have many possibility, out of which we get n initial equal to 2 by assuming that if lambda is longest, energy must be minimum, shortest difference of. So 1 by n initial square, यानी 1 by का square minus 1 by n final, 1 का square. So 1 by lambda longest will be equal to r 1 by 4 minus 1. So 1 by lambda will be equal to r minus 3 by 4, and so lambda longest will be equal to 4 by 3r negatives. Okay. For lambda should be shortest, energy difference must be maximum. So n final is equal to infinity. So it will be equal to r 1 by n initial square, means 1 by infinity, minus 1 by n final square, means r 0 minus 1 minus 1 minus r 1 by lambda shortest. So lambda shortest is equal to minus. All infinite lines of Lyman series must be lie between these two lambda shortest and lambda longest, that is in between 4 by 3r to 1 by r. Similarly, we can calculate the series limit of Balmer series, Parsons series, Brackett series, and Humphrey series. One more important thing is derivation of energy of nth orbit. En is equal to minus mz square e per power 4 8 epsilon square n square h square. This is the total mechanical energy of electron in nth orbit. But during derivation, we get total energy, mechanical energy of nth orbit was equal to kinetic energy plus electrostatic potential energy. After putting the value of V and R, the value was m z square e per power 4 8 epsilon square n square h square minus m z square e per power 4 4 epsilon square n square h square, and finally we get minus mz square e per power 4 8 epsilon square n square h square. Let us consider the case. Let us consider the case. This is the kinetic energy, and this is electrostatic potential energy of electron in nth orbit, and this is the total energy. One more important conclusion derived: kinetic energy has half the value of electrostatic potential energy with opposite sign. पोटेंशियल एनर्जी काइनेटिक एनर्जी का दुगना है, साइन क्या है? अपोजिट. सिमिलरली kinetic energy has equal value as total energy but with opposite, and total energy is half of electrostatic potential energy with same. means total energy of electron in nth orbit is half of electrostatic potential energy with the same sign. That is, total energy into 2 is equal to electrostatic potential. Similarly, kinetic energy and total energy has similar value. Total energy is equal to kinetic energy of electron, but sign is opposite. Total energy and kinetic energy has equal value, but with opposite sign. And the third most important thing is kinetic energy is half of electrostatic potential energy, but with opposite sign. That is, K is equal to electrostatic potential energy, but with negative sign. This is the most important three conclusions are there. And during solving the question, already we have the formulae. Energy of an nth orbit is equal to z square by n square minus 13 point. And if anyone asks, what is the potential energy of electron in fifth orbit? Right? What is kinetic energy of electron in fifth orbit? We can calculate. And what is total energy of electron in fifth orbit? The simple and unique only. So we can correlate kinetic energy, potential energy, and total energy of electron in nth orbit. After these two derivations, Bohr's atomic model was accepted because the wavelength calculated from Bohr's atomic model has almost exact value which was experimentally observed, and hence Bohr's atomic model was accepted. But just after acceptance of Bohr's atomic model, two observations goes against the Bohr. First observation was a splitting of a spectral line, a splitting of a spectral lines in electric field and magnetic field. Electric field and magnetic field was not explained by Bohr. That is a Stark's effect and a Zeeman effect, not explained, which was experimentally observed fact. And second one, Heisenberg's uncertainty principle. And as we know, Heisenberg's uncertainty principle is the severest blow on Bohr's atomic model. Severest blow. The reason behind the split Bohr could not explain the splitting of energy was they defined perfect stationary orbit cell, and there was no concept of subcell within a cell. And this hyperline fine line is separated with each other closely was only due to presence of a subcell within a cell. Subcell within a cell resulting in greater number of spectral line as expected by us, as expected by people, as expected by Bohr. उन्होंने एक्सपेक्ट किया कि सेकंड थर्ड से सेकंड में आने पर एक ही लाइन होना चाहिए क्योंकि एक एनर्जी गैप है, लेकिन इन रियल देयर आर मेनी लाइंस which is closely associated with. And Heisenberg's already explained, verified experimentally that any charged particle having extremely a small mass, or neutral particle maybe, any particle having extremely a small mass, if moving with extremely high speed, then practically it is impossible to measure their position and momentum 100% accurately. There must be some uncertainty in measurement of momentum and position, and the overall uncertainty either greater than or equal to h by 4 pi. Minimum uncertainty is h by 4 pi. Uncertainty may be more than that depending on observer error and depending on apparatus error. So if delta P is change in momentum, that is m delta V, so delta T into delta X, uncertainty in velocity, so uncertainty plus uncertainty in position is equal to h by 4 pi m. And this is the Heisenberg's uncertainty principle. If uncertainty in velocity given, we can calculate the uncertainty in position and vice versa. So this was the major drawback of Rutherford, Bohr's atomic model. But Bohr successfully explained wavelength of hydrogen spectra, and that's why this was accepted. So hydrogen spectra now can memorize as if electron finally jumps to 1, 3, and so on. Four, five, six. All lines of Lyman series, as we have already discussed in previous class, lies in ultraviolet region. Ultraviolet region of electromagnetic spectra. The lines of Balmer series lies in visible region, and lines of Paschen series bracket Humphrey in infrared. This is due to energy difference. Of course, we list the number of orbit equidistantly, but as difference between number of orbit increases, number of cell increases, energy difference decreases, and finally line appears to coincide in it with each other, and a thick band of different energy level, thick band of electromagnetic radiation will be there. So this is the hydrogen spectra and Bohr's atomic model. In next class, we'll discuss some of important numericals asked in different competitive examination from Bohr's atomic hydrogen spectra, and then one short video posted for quantum mechanical model of atom. Quantum numbers extremely important. अभी हम लोग कुछ नहीं, अगले 30-35 वीडियो में जितने भी जेई एडवांस के लिए इंपॉर्टेंट टॉपिक्स हैं उसको हम लोग कवर करने जा रहे हैं. So these topics are not for 11th and 12th studying student, but of course they can revise, they can get information from this video lecture, and we will soon start the separate video lecture series for pre-foundation and foundation also. But most of the students who got better percentile in JEE Mains now preparing for advance will get benefited from my video. Thank you very much. Thank you.